Okay, first up, ionic bonding.
Okay.
So, you know how table salt stays solid even
Yes.
when you heat it?
It's pretty amazing, isn't it?
Yeah. It's not magic, it's ionic bonding.
It is.
But what's actually going on at the atomic level?
Well, it all comes down to electrons.
Okay.
Those tiny little particles that are whizzing around the nucleus of an atom.
Right.
And atoms, they're happiest when their outermost electron shell is full. It's like
Yeah.
a perfect Zen state, you know?
Like completing a puzzle.
Exactly. Gotcha.
So some atoms, to achieve this perfect Zen state, they give or take electrons from others.
Okay.
And that forms what we call ions.
So some atoms are more generous than others, I guess?
Yeah, exactly. Like metals, for example, sodium.
Okay.
They have a few extra electrons in their outer shell, and they are happy to donate them.
Right.
They're kind of like the philanthropists of the atomic world.
I like that.
Yeah. And then, on the other hand, we have nonmetals. Chlorine's a good example.
Okay.
They're just a few electrons shy of a full outer shell, and they are very willing to accept these electron donations.
And so it's kind of like a perfect match made in chemistry heaven.
Yes.
The metal gives and the non-metal receives.
That's exactly it. So when sodium, for example, gives up an electron, it becomes positively charged.
Okay.
And chlorine, after snagging that extra electron, becomes negatively charged. And you know how it is with magnets?
Opposites attract.
Exactly.
Yeah.
And this powerful attraction between oppositely charged ions, we call that an ionic bond.
So it's more than just a casual fling. It's a serious, committed bond.
Absolutely.
Yeah.
And this bond doesn't just create a single pair of ions, it goes on to form a much bigger structure. A giant, what we call an ionic lattice.
Okay.
It's kind of like if you imagine a really well-organized three-dimensional chessboard where each positive ion is surrounded by negative ions and vice versa.
So it's like a massive microscopic crystal.
Yeah, you got it. And this incredibly strong and ordered arrangement gives ionic compounds some pretty cool properties.
Okay.
Like, think about how much heat it takes to melt salt. That's because those bonds, those ionic bonds, are so strong, they need a lot of energy to break.
So something as simple as table salt has all this going on.
Yeah.
All this complexity.
Exactly.
Yeah.
But it's not just about the strength, it's also about their ability to conduct electricity.
Oh, right, the ions.
Yes.
They can conduct electricity.
Exactly. But there's a catch, right?
Yeah.
They can only do it when they're free to move around. So when the ionic compound is melted or dissolved in water.
So it's like they're suddenly free to move around.
Yeah, exactly.
And do their thing.
Exactly. So when an ionic compound is solid, all the ions are held in place.
Stuck.
Yeah, exactly. It's like being stuck in a crowded room, but when it's melted or dissolved.
It's party time.
Yeah, exactly. They break free, move around, and they can carry an electrical current.
Amazing. So tiny particles creating strong bonds, forming complex structures, and then conducting electricity.
It's pretty wild, isn't it?
Yeah, ionic bonding is way more dynamic than I ever thought.
It really is.
It's really cool. So that's ionic bonding.
Yeah.
We've learned about how atoms try to get a full outer shell of electrons, how metals and nonmetals form ions,
Yes.
how that attraction creates that ionic lattice structure, and all the properties that come with it.
Yep.
But stay tuned, because we're going to explore another cool concept.
Oh.
Changes of state.
Looking forward to that one.